All right, folks, let's wrap up chapter 15. So this is going to be the descending motor pathways. So let's get this motor, these efferent descending. Let me just get all the words on here. Motor pathways are efferent. These pathways are descending. They're going out of the brain down the spinal cord. Descending. They're motor. Some of them are um, involuntary. Some of them are voluntary. So these descending efferent motor pathways. There's always at least two motor neurons, as it says right here. There's at least an upper motor neuron and a lower motor neuron. All right. Now we have two major pathways. We have a pyramidal pathway and we have a extrapyramidal pathway, and you'll see that in another slide here shortly. But what I'm looking at here, I better explain this. Extrapyramidal. The pyramidal pathways, the cortical spinal pathways, are pyramidal pathways, and they are voluntary pathways. Now, having said that, let me just tell you that some of the pathways in the cortical spinal pathway are at a subconscious level. I'm not going to pretend that they're all this conscious muscle contraction level. They're not. But these cortical spinal pyramidal pathways are, typically speaking, these voluntary conscious pathways. And these are extrapyramidal pathways, and we'll talk about the extrapyramidal system as well. And by the way, these are integrated. It's not like one happens or the other happens. Of course, as you probably are aware of already, things aren't as simple as we look at them in the beginning. There's all this integration going on. All right, so the direct pathways are the pyramidal pathways. All right, so this is the pyramidal pathway. They're called a direct pathway. They are the cortical spinal pathways. That's what they are, the cortical spinal pathways. The cortical spinal starts in the cortex and goes through the spine. You can see that we have two subdivisions of the cortical spinal pathways. We have the anterior cortical spinal pathway and we have the lateral cortical spinal pathway. That's similar to the ascending spinal thalamics, where we had an anterior and a lateral. All right. So those are the direct pathways. And this is, typically speaking, okay, so you see muscle tone here. A lot of your muscle tone is at a subconscious level. It has to do with posture and tone, etc. But you can see here that speed and precision of skilled movements. All right, that's going to be a voluntary system. Now we have these indirect pathways. This is called the extrapyramidal system, the indirect pathways. This is an older pathway. It's a lot of reflexes in this pathway. When I say older, I mean evolutionarily older. The indirect pathway is evolutionarily older. And you can see that these indirect pathways are broken up into the rubrospinal, the reticulospinal, the vestibulospinal, the tectospinal. You know these, all right? Let me prove to you know these. Rubrospinal should sound to you like red spine. Well, it comes from the red nucleus of the midbrain. Remember the red nucleus? It was red because it had a great deal of blood flow and a lot of myoglobin and hemoglobin. So it comes from the red nucleus and goes down the spine, the rubrospinal pathway. The reticulospinal pathway, the reticular formation. Reticular formation. Now you got to remember the reticular formation is a diffuse area. I shouldn't have said reticulo formation. I'm sorry. It's the reticular formation. It's a diffuse area. It's partly found in the medulla oblongata. It's partly in the pons. It runs up and down through the brainstem like that. The vestibulospinal pathway. Well, what the vestibulo indicates is balance, the vestibular apparatus of the inner ear. And indeed, that's what this does. The vestibulospinal pathway sends information from the inner ear, from the vestibulocochlear nerve, in other words, to the cerebellum for one thing, and to some postural muscles for another. And it all has to do with your balance. And the tectospinal. Tectospinal, if you remember what the tectum is, the tectum was the roof of the midbrain. If you remember what the midbrain is, the midbrain was the cerebral peduncles, the corpora quadrigemina. The cerebral peduncles and the corpora quadrigemina. However, when you cut the midbrain, when you cut it in a cross section, you saw you had a substantia nigra, and you had a red nucleus, and you had these other areas within there. Well, the tectospinal pathway comes from the tectum and goes down the spine. So these are the indirect pathways, and we'll look at each of them. This is, again, just an anatomy picture showing you that. You're not going to have to memorize where these are located. Okay, you will not. Just so you know, just so you're aware, that these dotted lines are the ascending pathways. This is the dorsal column medial lemniscus pathway. This is the spinocerebellar pathway, the posterior spinocerebellar pathway. This is the anterior spinocerebellar pathway. This is the anterior spinal thalamic pathway. This is the lateral spinal thalamic pathway. So the dotted line areas are just superimposing without jumping out at you the ascending pathways. Now, when you take these descending pathways and these ascending pathways together, you can see that the white matter of the spinal cord is pretty much all used up. So you can see that here. So again, the dotted lines are just showing you the ascending pathways, and they made it dotted and uncolored so it didn't make the slide too busy. You're probably saying it's too busy anyway. Well, it is kind of busy, but you can see the dotted lines, which are the ascending sensory pathways. And when you put them all together, you can see that our white matter is pretty busy. All right, now here's a pathway. Let's look at the upper and lower motor neurons first, all right? First of all, coming from where? What is this primary motor cortex? And the answer is it's the precentral gyrus. Precentral gyrus. Coming from the precentral gyrus, the primary motor cortex, I have this upper motor neuron. All right, here's my upper motor neuron going down through the internal capsule, down through the cerebral peduncle, down through the medulla oblongata. Many, many, many of these fibers decussate in the medulla oblongata. They actually decussate at the pyramids. We call this the decussation of the pyramids. Now, if I were to say to you, do they all decussate at the pyramids? The answer is no. Look at this one. This one stays ipsilateral for a while and then decussates later. So not 100% of them decussate in the medulla oblongata, but many of them do. All right, so here's the decussation of the pyramids. They decussate, they come across, and they travel down through. And then they eventually synapse with the second order. The lower motor neuron, second order. That's a term used for sensory. We have upper motor neurons and lower motor neurons. So now my upper motor neuron is synapsing with my lower motor neuron. And my motor lower neuron, as you can imagine, leaves through my anterior root, my ventral root. Remember, my sensories go through my dorsal root and my motors go out my ventral root. Leave through my ventral root and go to the skeletal muscle and say contract. All right, so this is an upper motor neuron and a lower motor neuron here. Now, basically, all of them, the pyramidals and the extrapyramidals, follow the same pattern. They follow the same darn pattern. However, where they decussate might change. What fasciculi and funiculi they run in changes. And you're going to say, well, which one do they run in? Well, go right back here. Look at all these fasciculi. So in the lateral column of the white matter, I have a rubrospinal tract. I have a lateral cortical spinal tract. Those are the fasciculi of the lateral column. In the anterior column, what do I have? I have a reticulospinal tract, I have a tectospinal tract, and I have a vestibulospinal tract. Those are the fasciculi of the anterior column funiculi. So you can see where they're running, and they all follow about this pattern right here. Right here. All right. Now, some of the motor neurons that serve the head, and probably head and neck, they will decussate and they'll decussate before the pyramids. They'll decussate prior to the pyramids, like in the midbrain, and then they'll go to the skeletal muscles. Or they can decussate in the medulla oblongata superior to the pyramids and go to skeletal muscles. These are going to be the cranial nerves that have motor function and go out to skeletal muscles of the head and neck and tell them what to do. They they go out and tell muscles of the head and neck what to do prior to the decussation of the pyramid, so they decussate and leave before that. All right. So that's the basic pattern of these lower motor neurons. Now, please, this is a summary. You need to know the cortical spinal pathway is the pyramidal pathway, and quite often it's a conscious level control. You need to know that. You don't have to break the cortical spinal pathways down into the cortical bulbar and lateral and anterior cortical spinals. Just know cortical spinal. All right. These are the extrapyramidal pathways. And again, you only have to know that the medial and lateral pathways are extrapyramidal and therefore largely subconscious level involuntary control. You don't have to break them down into all of these right here. Although I did tell you how they're named. I said, tecto comes from the tectome, rubro comes from the red nuclei, vestibulo comes from the vestibular nuclei of the pons and medulla oblongata, which came from the vestibulocochlear nerve of the inner ear. So you can see that. All right. Now, the comparator diagram of the cerebellum. By the way, this is probably, I think this is the picture in your book. I gave you this one because it's better. It's less busy. So I'll talk to this one, then just show you the one that you're probably going to have in your book. The comparator diagram describes what the cerebellum does for us. And so before I go through some of these arrows, the cerebellum right here basically compares what your motor cortex is trying to do with what is actually happening, and then modifies it. Keeps you in balance, keeps you coordinated. All right, so let's start in the beginning. In your premotor area of your frontal lobe, you make a plan to do a muscular movement to jump over the candlestick. That's by the way, in the prefrontal cortex, you got the motivation to jump over the candlestick. Now, for some reason, you want to jump over a candlestick. I don't know why, but you do because you have the motivation to do it. So your prefrontal cortex gave you the motivation to jump over the candlestick. The premotor area put the plan together how to jump over the candlestick. And then that sent it to the prefrontal, the precentral gyrus, and that started executing the plan. Okay, so number one is the precentral gyrus sends out the signals to execute the motor plan. Here we go. We have an upper motor neuron coming down through, and we synapse with a lower motor neuron, and that goes to the skeletal muscles. Now, you have a lot of parallel fibers here because obviously you're going to be contracting more than one skeletal muscle at a time. All right. That's the plan. That's the execution of the plan. You have the upper motor neuron. You have the lower motor neuron. So far, no problem. All right. Meanwhile, just so you know, the plan was sent to the cerebellum. The cerebellum knows what your plan is. All right. That's what the cerebellum knows. Excuse me. If there's anything that's procedural memory in that plan, now I know we haven't done memory yet, but there's really two classes of memory. There's declarative memory where you remember a fact or basically a fact, and then there's procedural memory where you remember how to do something, like you never forget to ride a bike. Procedural memory. If any part of this plan is procedural memory, what you'll do is you'll have a descending pathway out of the cerebellum. It goes through the red nucleus. So guess what? It goes down through the rubrospinal tract. That's the rubrospinal tract. And you will execute those, you will contract those skeletal muscles based on your procedural memory. You won't have to have you can actually take away some of this conscious level control if the plan has some procedural memory involved in it. Okay? And by the way, the cerebellum told your motor cortex that some of this was procedural memory. So there is actually a positive feedback loop here where your motor cortex knows that some of this is procedural memory and it's going to be enhanced. Meanwhile, your skeletal muscles are contracting and your joints are moving. Bones around your joints are moving. The Pacinian corpuscle, Golgi tendon organs, and muscle spindles of those joints send signals back to the cerebellum via the spinal cerebellar pathways. And your cerebellum checks to see, is anything going on that is not going according to plan. It tells the motor cortex if anything is going on, anything going on, not according to plan. And it will automatically modify it if it has to. And so you're going to say, well, what's the example of that? Well, the example is that, let's say you're walking down the stairs at night, you didn't turn a light on, and you thought you were on the ground floor or the bottom of the stairs, but you weren't. You were actually one stair up still. Well, your mind had a plan how to walk to the fridge, but there was a curveball in the way. You weren't on the bottom floor yet. You still had a step to go. Well, you step out like you're on the bottom floor, and all of a sudden you start to fall because you are actually stepping down the last staircase. Well, you're young and you have good muscle tone, and your brain is sharp, and you catch yourself. Okay, so I used to catch myself, but nowadays I fall. And we're going to talk about aging, and at the end of this, we can talk about aging later, aging in the nervous system later. But everything's going well, and your cerebellum catches you, and your motor cortex know that that's what happened. You probably laughed at yourself because you caught yourself. I mean, the information went back to your motor cortex, of course. And you readjusted the plan because you have to readjust the plan. You just had to catch yourself. But you caught yourself. That's because the cerebellum had this comparator function. It compares what the plan is and the execution of the plan to what is happening in reality. You're not off this last staircase yet, and it modifies your movements and keeps you in balance and coordination. That's the comparator diagram. All right. Now, this is also a comparator diagram. Believe it or not, it shows you the same thing. It does add a couple levels to what I just told you. It shows you the rubrospinal tract. It shows you the reticulospinal tract. It shows you the vestibulospinal tract. All right, it shows you these tracts. But really, these are no different than what I showed you because the cerebellum feeds into these. And you can see the cerebellum feeding into these. All right. So the cerebellum simply utilizes these tracts to modify your movement if things aren't going according to plan. And that's all. Whew. Okay. So this is really just a comparator diagram, just not as simple